Welcome to the Astronomers for Planet Earth webinar series, hosted by Dr. Travis Rector, Professor of Astrophysics at University of Alaska, Anchorage. Today's guest is Rosemary Barnes. Rosemary is a mechanical engineer and consultant in technology development and innovation strategy. While being an expert in renewable energy and sustainability, Rosemary also enjoys communicating about these topics and climate change. Her YouTube channel, Engineering with Rosie, is a great example. With her work, Rosemary is also encouraging young people, especially girls, to engage in engineering to tackle the world's biggest challenges.
Hi, everyone. My name is Travis Rector, and I'm a professor of physics and astronomy at the University of Alaska, Anchorage. And I'm also one of the organizers for a group called Astronomers for Planet Earth, which is a group of professional astronomers, educators, and students who are working to address the issue of climate change. And today I'm especially happy to have Rosie Barnes, who is a mechanical engineer who also works in renewable energies. And I first discovered Rosie from her YouTube channel, which is called Engineering with Rosie, and it is awesome. And I highly recommend that you check it out after you watch this video. I found it, her style is really great for explaining a lot of the energy solutions that we're going to need to address the climate crisis. And so, Rosie, thank you so much for being here today. We really appreciate it.
Well, thank you for inviting me. Okay, so yeah, thanks for that, Travis, and thank you very much for having me. My name is Rosemary Barnes. I'm an engineer working on clean energy technologies, and today I'm going to talk about the transition from renewables to fossil fuels way back before the Industrial Revolution, just really quickly about that part. And then I'm going to talk about our current transition back again to renewables, and then moving forward, what challenges remain and how I think that we're going to be able to solve them. So I'm going to start way back in the past and talk about how our energy system has responded to our needs and desires and how different technologies have been able to provide those needs in 4 categories. So these categories are availability, scale, cost, and climate change. So let's start way back with early humans. So they used what was available to them. And back then that was all renewable resources. There was biomass for cooking and heating, also wind and solar for preserving food. So that top left picture I took when I was on a ski holiday in Norway, and they're still preserving fish in the traditional way using the solar energy and the dry wind to preserve it. Then we've got a picture of the pyramids, and even way back then, they knew about solar energy and how to design their buildings so that they could use the solar energy to heat their homes. Of course, everybody knows about wind energy being used for transport in sailing ships. And then later on, people were using windmills and hydropower for mechanical power to like grind grain and help with other mechanical power requirements. Okay, so next we come to the first energy transition, when we discovered that we could dig up coal, and that provided a very concentrated form of energy that could be transported and stored far more easily than any of the sources that had come before. And it also allowed the development of the steam engine, which pretty much kickstarted the Industrial Revolution. So all of a sudden, much more energy was available, and it did cost more than the free energy that it was replacing, but it added so much more value that overall, really allowed the economic activity to just massively increase really, really quite suddenly. So there were some downsides too. Some of them were immediately obvious, like soot and illness, and then some of the other externalities would take longer to show their consequences. So this is that famous NASA map of global temperatures. And yeah, obviously by, I don't know, I guess it depends, 80s, 90s, it was becoming pretty clear that the planet was getting warmer than it had been before. And yeah, I mean, it's pretty clear when you look at it, all of the images on that graph. But yeah, by now, I think it's obvious our lived experience that the planet is warming. I mean, for me personally, it's been a really long time since I really thought much about the science, because it was so obvious so long ago that I pretty much just had my head down working on solutions to this problem since, like the 2000s. Okay, so now I want to skip ahead to electrification, which was happening in most of the big cities around the turn of the 20th century, obviously a bit earlier in some places, a bit later in others, and still happening in developing countries now. And once again, we saw that the type of power used was chosen based on what was available. So for the most part, countries electrified using large centralized fossil fuel power plants, like that one there, that's an Edison power plant. It was one of the first in the world in New York. They use these large centralized fossil fuel power plants, not just for electricity, but also for heat and transport and industry too. So economies really built on the basis of cheap and available fossil fuels. When high voltage power lines were introduced, then that was a big development, because it meant that electricity could be transported now further away from the generation source. More people got access to electricity, and it also meant you didn't need to have those really dirty, sooty fossil fuel power plants right in the cities. So for most countries, fossil fuels were the easiest way to generate electricity, because it can be transported and it can be stored. But where really good renewable resources were available, then that's what they used. So examples of places that use a lot of renewables right from the start, places with a lot of mountains and water, like Norway and Quebec, who used a lot of hydro. Rural Denmark electrified first using wind energy, which is a really interesting story in itself. That picture at the bottom left is one turbine that was made from a Danish engineer, Paul Lecour. He was a teacher. He wanted to, Denmark is a very dark place, especially in winter, as I have personal experience with. I lived there for 5 years. And it's also a very windy place. And around the time, like, big cities were electrifying, but in rural Denmark, they weren't getting electricity anytime soon. And Paul Lecour, this teacher, he wanted lights to be able to teach his evening classes to adults in rural Jutland. So he actually did a lot of research on wind turbines, and he had the idea that, well, Denmark is such a windy place, we should be able to use this energy to make electricity. And so he did. He made some wind turbines. He did a lot of work on making them more efficient, figured out that fewer blades would actually make a more efficient wind turbine. And he was actually using it to make hydrogen and to power lights on hydrogen. So that's kind of a really interesting today, when we're, kind of back to the future with going back to that idea of hydrogen as being a good way to store energy. So those are the two main renewable sources that have been used for a long time. There's also geothermal. Iceland gets a significant share of their power from geothermal. Back, like 100 years ago, the geothermal was just used for heating, but now they use it for both. And geothermal and hydro, they also have that real big advantage that they really are a lot like fossil fuel power in the way that you can use it. You can turn it on and off when you want. It's not like wind and solar, where you do have that issue of variability. Okay, so so these are the countries that kind of were into renewables before they were cool. That other than the smog and illness and the environmental destruction and conflict that fossil fuel resources can cause, most of the world was pretty happy to just continue, like all in on their bet on fossil fuels, until the 1970s was about the first time that people thought, oh, wait a minute, fossil fuels aren't necessarily always going to be super cheap. So there was, the oil crisis in the 1970s, and prices went up. And I'm going to talk a lot about that. I'm no economist, but it did have a really big impact on a lot of the renewable energy technologies, because at this time we saw a resurgence of research into renewables, and especially wind energy, because at that time that was the most mature of the non-hydro, non-geothermal energy sources, because obviously you can't, like everywhere has some wind, but not everywhere has a location that's suitable for making hydropower or geothermal. So the US did a lot of research and development, including a lot of effort to try and make vertical axis wind turbines work. And so those are the ones you can see on the left there. That's a like egg beater design that was pretty common for the attempts to make big industrial vertical axis wind turbines. On paper, a vertical axis wind turbine has a lot of advantages. And so in those early days, while people were still trying to figure out what works in practice rather than just in theory, there were a lot of people that were putting effort into the vertical axis wind turbines. You can kind of see some of the disadvantages in that picture. They've got all those guy wires there, which are a bit complicated, and you need that to kind of keep everything stable. And in the end, that was more or less a dead end for industrial scale technology. Then on the right-hand side, we have a wind turbine in Denmark in a small town called Tvin. And that's a photo I took myself when I visited it. It was built in 1978, it was commissioned in 1978, but it's actually got a really interesting backstory because Denmark was having the same energy crisis that everybody was having in the 70s. They were pretty keen on energy independence. And so they were starting to make plans that involved a lot of nuclear power. And so this group of teachers in Tvin, and I've heard them called hippies, a bunch of hippies by a lot of people call them that, they wanted to demonstrate that one, wind energy could be an alternative to nuclear, and two, that it could be done with people power. That was their whole thing. Nuclear power needs specialized people, needs to be mandated by the government, very controlled. And they actually got a group of hundreds of volunteers together to build this wind turbine. It was, at the time, way bigger than anything else available. It was the world's first multi-megawatt wind turbine. And more than 40 years later, it's like 43 years since it was commissioned, it's still operating now, more than 40 years later. So I think that is a pretty good indication of people power. And one other thing that was kind of that this particular project impacted on the rest of the industry was that it was all open source. There was no design secrets or anything. So everybody could learn from the experiences of that project and make better wind turbines afterwards. So after the oil crisis, most countries kind of went pretty quickly back to fossil fuels when the price went down again, and they pretty much forgot about renewables, but not in Denmark. They continued to support wind energy, initially because of the energy security thing. They didn't have a lot of fossil fuel resources there themselves, and the people had spoken out against nuclear. So they had targets for energy production right through, and they also had a policy to reduce CO2 emissions quite early compared to other countries. So I think even in the 1980s they had a CO2 reduction policy, which is definitely well before it was on my radar, and most countries, I think. So this series of pictures is the ones that I took all in Jutland while I was in the first lockdown that we had, and I had some time on my hand to drive around, and you can see all of the design evolution, all the different things people were trying out when it was at that really interesting period in the technology life cycle when you still don't know what's the right thing that's going to work. So we saw, people have been trying vertical axis wind turbines out. It wasn't as easy to do in practice. And here's some different ideas that they had for wind. And then eventually it kind of all settled on the one on the far right, or the last couple look really similar to wind turbines that you see everywhere now. And that's sometimes called the Danish design, which is 3 blades. The blades are downwind. The blades are upwind of the tower. Those are the 2 main things that kind of Denmark settled on, and pretty much everybody else has followed that too. Okay, so other than in Denmark, no one else is really focused on wind energy at that time. A little bit in California for a while, which helped the Danish industry to keep going, but not much else apart from that. Until I'll say about the 1990s is when people really started to take the idea of climate change seriously. Obviously, some people knew it was a problem before then, some people didn't take it seriously until much later. But about the 1990s, people did start talking more about climate change. And then research started again on renewables. So by this time, solar power, photovoltaics, the technology had come far enough that it could be imagined to play a role in the energy system, not just for tiny niche applications like it had been in the decades before. It was much more like a science thing rather than, an actual part of the energy system. Wave energy was also getting a fair bit of research attention, and the wind continued. Wind was still probably the most mature technology by then. So it was in the 1990s that we saw the first offshore wind farm in Vindeby in Denmark. That's what that picture is of. It was made up of 450 kilowatt turbines, so very small by today's standards. I mean, the offshore wind turbines now are, like 15 times bigger than that. Oh, no, more, like 30 times bigger than that. So things have changed, but they look roughly the same. And this wind farm was only decommissioned in 2017, so it had a pretty good long life. And then in the 1990s, another significant thing that happened was in the US, the National Renewable Energy Laboratory was established in that same year. And anybody who works on renewable energy technology or probably anything else to do with renewable energy all around the world just loves NREL because they publish so much information open source, and that it really allows people to stand on the shoulders of the giants before. If all the research is just done in companies, then you can't so much learn from previous people's mistakes. So I definitely appreciate that agency. So still though, in the 1990s, it was hard to imagine renewables could ever actually replace fossil fuels because of cost. So this chart shows the price of solar modules, and in the 90s, they were still between like $5 or $10 per watt for a panel. And you compare that now, it's like cents, and then we'll see this one's the levelized cost of energy, comparing a bunch of different technologies. So wind was the only major renewable at that time. So it's around, like 15 to 20 cents a kilowatt hour. And then you can see, it's hard to see, but on that chart, you can also see the line of the fossil fuels price range. So in the 90s, wind was maybe just like competitive with the very worst, very most expensive fossil fuels. And you can see the fossil fuels, like cheap fossil fuels are way down here. And yeah, so around that time, it really did seem hard to imagine that ever spending the amount of money that would be required to just totally replace the energy system from fossil fuels to renewables. And I also wanted to point out that this graph shows the amount of generation by source, and the red is renewables, non-hydro renewables. And you can see, in the 1990s, it's like it barely registers as, it's barely even visible on the chart. So that was kind of, I don't know, if you were a climate scientist at that time, I could see how you would be very upset about the scale of the problem and the likelihood that we would ever actually, pay the price necessary to change over to renewables. So now let's move over to 2000s. So this is kind of where my personal interest started. This is the time that I was going to university and then getting my first job. And I guess the thrust of the 2000s for me, the way that I see it for renewable energy technology, is that it was just about getting costs down. It was just like relentlessly driving costs down. I started working in 2005, and I worked for a few renewable energy startups, and actually including a couple of those technologies that you can see there. And at the time, I remember all my colleagues, there was other greenies and hippies, people who thought that the planet's climate was more important than cheap energy, like such a radical concept that, it's important to have a habitable planet. But it wasn't just like I don't know, serious business people and engineers who, just wanted to work on a saleable product. It was predominantly people that really were passionate about the cause. And so the companies that I was working on, they were getting a lot of research grants, working on really new technologies. And it was really exciting to be working with the research and cutting edge, but at the same time, most of the companies I would work with, you'd kind of get a sense that there was no business case once the government grants ran out, that it was really hard to imagine it, surviving, and also hard to imagine the scale. And so I was working in renewable energy, but I didn't really feel like I was actually contributing anything to solving climate change, because no green electrons ever got produced because of the work that I was doing back then. And every company that I worked with eventually failed, although one or two of them, their technology has kind of lived on through some sort of, splintered company. So, and I think that that's kind of quite indicative still about how these early stage renewables go. And it's one of the things that drove my my next career step. I also wanted to talk about what was happening with batteries at that time, because in the 2000s, no one was really thinking about batteries with respect to energy, but we did now all of a sudden have mobile phones and laptops, which were very exciting and made possible by lithium-ion batteries. And then you can see on the right, I've put a chart of the price of lithium-ion batteries. And you can see in the 2000s, they were dropping a lot because of this consumer products. Yeah. So then something else happened in the 2000s that was kind of big. We had the GFC, the global financial crisis. And I remember the company I was working for at that time, it was like the rug had been pulled out from underneath us, So I mentioned that we were very reliant on government grants, and also people feeling like a bit of a warm and fuzzy feeling from investing in renewables. And when the GFC happened, people were not as worried about feeling warm and fuzzy anymore. They were worried about, finding a new job, and they were worried. The government wasn't really worried about climate change. They were worried about, getting people jobs and getting the economy back on track. So I can remember how deflating it felt at that time as research budgets got cut, and it didn't seem like many people cared about the climate at all compared to their economy. And we did see a lot of public money being spent to stimulate the economy, but it didn't really go to renewable energy or other climate change programs. So for me, around that time, I started getting really quite depressed about the politics related to climate change in the whole world, but especially in Australia. And I decided that I didn't want to work on these small scale technologies that would likely never go anywhere. I just felt a need to work on something that was having an impact, actually making green energy. And I didn't think that we would ever prioritize climate change because it's the right thing to do. I felt like I needed to work on getting renewable energy cheaper so that it would become an economic decision instead of a moral one. I was really quite depressed at that time and feeling very pessimistic about the world ever doing the right thing. And so that's why I made the decision to go back to university. I got a PhD that I hoped would allow me to get a job at a major wind energy company, because mostly I chose wind energy because I have interest and skills in composite materials, and also an aero background, but also it was the most mature, largest, most easy to imagine scalable energy technology that we had at that time. So so I did that, and I joined the team of renewable energy engineers around the world that just focused relentlessly on getting costs down on a scalable technology. So then this is a chart. I just wanted to quickly bring up the concept of the levelized cost of energy, because that's kind of been something that we've been very focused on as a way to, compare the cost of energy between fossil fuels and renewables. So the levelized cost of energy, it just divides the total cost of the whole lifetime of an energy project divided by the total energy that it makes. So you get a dollars per megawatt hour or dollars per kilowatt hour figure. And when you see, how much energy technology costs in the, reported in the media, it's usually always this LCOE. And there's definitely problems with this way of calculating, but before we started using that measure, it was really hard to say what's cheaper or not, because, for example, the capital cost, equipment cost of a wind turbine is more than the same amount of energy for a gas turbine, but then the energy is free for a wind turbine. So it's hard to, kind of get an overall sense. And so this is the way that we did it. And then we've got that same graph that I showed before about the cost of energy coming down, and with the bands for fossil fuels, the high end and the low end. And so you can see around the 2000s, we start to get in that range. And so that was kind of like the buzzword for the 2010s was grid parity. So grid parity is when the renewable energy gets as cheap as the fossil fuel alternative. And this map shows when solar power reached grid parity in some countries around the world. So the green countries reached grid parity for solar power before 2014. And you can see, here in Australia, where I'm from, we were one of the early ones because there is so much sun here. Not this spring. It has been very, very rainy, which is upsetting for me because I just moved back. And then the colours are, this teal colour is countries that reached grid parity after 2014, and then some other colours about, because the price of energy, it changes. And so it's not like a simple matter of, oh, now it's cheaper. It could be like, now it's cheaper in the evenings, but not in the mornings or something like that. So then we've reached that point of grid parity. And so that was good. And I remember we reached the point of grid parity, and immediately in Australia, the government started suggesting subsidising coal power plants. And I was just like, oh, for God's sake, it's not even enough to make it cheaper. There's more battles to be faced to get renewables to replace fossil fuels. So then after grid parity, the next thing is to reach grid parity for the marginal cost of conventional generation. So in that LCOE formula, you've got the cost of the equipment in there, but after a certain amount of time, your fossil fuel power plant has paid off its capital costs. So now you're just worried about, should we keep running the power plant? So it's like the cost of the fuel and the variable maintenance costs that you have to maintain it more if you use it more. And this is a current graph from Lazard, who they do updated ranges for the levelized cost of energy for a range of technologies. They do it every year. So this one's new, and it's about the marginal cost. So you can see on the left, you've got the levelized cost of new build wind and solar, and then on the right, the marginal cost of conventional generation. So a coal power plant that already exists, should you keep on using it? And you can see that just the marginal cost of coal is already more expensive in many cases than lots of renewables. And for the other kinds of fossil fuels, and for nuclear, it's in some cases cheaper to build a new wind turbine or a new solar farm than it is to just keep on operating the coal power plants. So it's a critical thing, because now you get to the point where it's worth shutting them down. It's not just, oh, if you need to build a new coal power plant, then you wouldn't. You would instead build, solar and wind. Now it's like, even if you have the technology, it's still cheaper to not use it and to build something else instead. So for me, this makes a huge difference to like the pace of the renewable energy transition. Before, when we were just at grid parity for new build, then it's like you have to wait for every single coal and gas power plant to retire before you would build anything new. But now we're at the point where it's like, no, like on an economic sense, it actually makes sense to move towards renewables. So now here we are in the 2020s, and I basically think that the cost and the scale, well, the cost has been more or less solved. The scale, maybe not solved, but the momentum is there. If you look at the installation for new solar and new wind, everything's on this kind of like nice exponential curve. The wheels are in motion, even for EVs and stuff as well. Like they're really, ramping up quickly. So I think that given that the economics are on side, that this is going to happen. And I also just included this graph here that shows the cost trends for different technologies. So you see the cost trend for solar has decreased the fastest. And then, onshore, so I should explain this graph a bit more probably. So you've got the levelized cost of energy on the y-axis, and the x-axis is the cumulative installed capacity, and I think it's a logarithmic scale. Yeah, it is. Because there's this technology trend where usually with every doubling of installed capacity, you get a pretty constant reduction in cost. So that's what these lines are showing. They call it the learning rate. So the way that you can expect cost, you can project into the future to see, when we double the capacity again, how much will it probably cost? So you see really nice reductions for solar and onshore wind. Offshore wind is less steep curve. And then it's got a couple of fossil fuels. Well, it's got coal, fossil fuel staying quite flat in its most recent doubling. And nuclear energy has actually gone up recently, largely because people are imposing more safety requirements on it than they used to. So I think it's clear to see that the trends that we've seen in the past of, the economics getting more favorable for renewables are set to continue into the future. And so that's why I say the scale, we don't have the scale we need yet, but we just I can't imagine that we're just all of a sudden going to stop increasing more and more the amount of renewables that we install each year. So that's the point I'm trying to make with that one. But it still leaves to two big questions on availability and on climate change. Here I just wanted to talk about some of the things to do with scale. So, we see so much rooftop solar, for example. In Australia, more than 1 in 4 houses have rooftop solar on them. And when you add up all the rooftop solar together, it's the biggest generator in Australia. And that's something that's mostly happened just because of 1, economics, and 2, because the people want it. And then I would say a distant third is government policy to encourage it. So that sort of makes me, I'm imagining a similar thing happening with many other renewable technologies into the future. I've also put a picture of an offshore wind farm there because for me that's a key part in the scale. We still do need many, many, many times more renewable electricity generation than we've got. And I don't see it all happening onshore. So I think that, technology development for offshore wind to get the prices down and roll it out more, that's going to be a key part in being able to get just enough renewable electricity out there. So I also just wanted to talk a little bit about COP26 and what I hear people saying, because as I've mentioned, I'm optimistic. I almost think that energy transition is unstoppable now, and I don't worry about the politics very much anymore. But I know when you read headlines about the COP26, or anytime you're reading about renewable energy or the climate change, I do feel like you get a lot of negative feedback, like we've done practically nothing. And, if we see projections that get referred to as business as usual that show us headed for, 5 or sometimes 8 degrees warming. And I don't want to get too much into the modeling. Maybe you've got some climate modelers in the audience which know much more about it than me. But I know that there's this scenario, the RCP 8.5, which a lot of people call business as usual. And I just will say from a technology point of view, it's not realistic. They take recent outcomes and extrapolate into the future, but that ignoring technology trends, these, technology and economic, especially forces that are just like a train in motion. If it's accelerating, you're not going to be able to stop that train from continuing to accelerate. It's already it's already happened, the thing that needed to happen, even if we don't see the effect in emissions reduction now. So I won't say too much more about that, but I think that there is a mismatch between the science and the engineering at one point. And if you want a more optimistic take on it, then I would recommend listening to some engineers about how it's going to work. And I have been insulted a few times, called a techno-optimist, like that's a bad thing. And I do want to say that it's not the same as, like a Scott Morrison, our Prime Minister, or even Bill Gates kind of techno-optimism, which kind of thinks, oh, there's going to be some magical technology solution in the future, so we don't need anything. It's not that at all. It's kind of the opposite. It's that we have the technologies that we need, and we do need to do something. What we need to do is, and what governments need to do, is to pave the way for these technologies to roll out as fast as possible. Because if you just let it roll out at the natural pace, it's too slow for for climate outcomes. Okay, so one other thing about the politics and the activism that I do appreciate how it's tied together with the technology. So I mentioned before in the GFC, when progress on renewables really stalled while economies tried to rebuild. But now we kind of have this nice interaction between the politics, activism, and the technology, where it's politically popular to act on climate change now. And then the economics, the technology is favorable enough that green tech can be used as a stimulus. So it's a massive difference now when we find ourselves again with public money being spent to stimulate the economy. Last time that happened in the GFC, it was just like, huge setback for renewables and the energy transition. And now it's kind of the opposite. So I feel really positive about how far we've come from there. And so I think it is, like a nice tying together of the engineering, the politics, the activism. It's all kind of, they all needed each other to get to this point, where we are now. And so that's all very nice. And I am feeling optimistic about how far our existing momentum is going to get us, but it won't get us to zero, because some sectors are simply never going to have better, cheaper, cleaner alternatives than the current emitting incumbents. And so for the last part now, I want to focus on the last couple of those four needs that I've been talking about: availability and climate change. So I've been focused mostly on electricity, both in my talk today and also throughout my career, because that's the biggest and the easiest path to to solving the energy transition. If we make our electricity supply green and then we electrify everything we can, then that does get us most of the way to zero. The solutions that I see are first, complementary sources. So we all know that solar, doesn't work when the sun goes down, and wind doesn't work when there's no wind. So you do a lot by having complementary sources. So you have solar, you have wind, maybe even some other new technologies like wave and tidal energy or airborne wind. I think there's a chance that they could play a role. But the most important part is to have geographic diversity and then connect them. So that's why I've got those power lines there. So you can imagine, if you can connect east to west, you get a much longer period when you've got solar power available in the grid, and also connecting up areas with different kinds of wind resources. So then the next thing that's going to help with availability is going to be load flexibility, which is something I'm a little bit obsessed with it, and it's not something you hear politicians talk about a lot. But our whole energy system, it was designed around fossil fuels, which run nonstop. And the way that we use energy now, we follow the load. So if people want to use electricity, then we generate to match that load. And I think there's a lot to be gained by kind of flipping that. And so saying there's a lot of electricity available now, let's use it. So some ways that you can do that are like big industrial users, like an aluminium smelter. In some cases, aluminium smelters can, make up like 10 or 20% of the whole grid's electricity demand. So you can see that if you can just modify that a little bit, it can have a big impact. And some of them are already doing that because they just save a whole lot of money that way. Another industrial user is a cold store. They can, if they know that the sun is about to set, for example, or that there's going to be a lull in the wind, you can predict that quite well, and then you can, just pre-cool so that you don't need the cooler running during the time where you don't have enough electricity available. Some other things that we can do is adding a lot of electric vehicles with smart chargers and flexible tariffs to get people in their homes using electricity at the times when it's cheap. And then there's a happy coincidence at the moment that when electricity is cheap, it's also usually very clean and renewable. So I think that the main challenge here is not the technology that's a problem, it's the markets aren't set up for that, regulations aren't set up for that. And it is complicated, and people have been trying for a while without a lot of success. So I'm not sure how much that's going to, of an impact that's going to have. But for example, as we add a lot more EVs, then we're definitely going to have to get smart about how they're charged, or it's going to cause huge problems. And if we do it clever, then we can actually have it be a solution. And then the last part of the availability problem is storage. So I've put there that center chart there. That's from a video that I did on electric vehicles, vehicle to grid technology. So you can use the batteries in cars to support the grid when they need it. And then it's really exciting time for energy storage at the moment. It's one of the technologies that, as an engineer, as a bit of a geek, this is probably what I'm most excited about, because it's like actually new technologies that are being developed. In many cases, they're actually really old technologies, but we just never had the need to use it on this scale yet. So that middle image is a gravity energy storage. So it lifts up concrete blocks and then drops them. So, that's like grandfather clocks have been doing that for hundreds and hundreds of years. And now here it is on a gigantic scale. This one here is off-river pumped hydro. So, we talked a lot about hydro, and it's been used, for, I don't know, probably thousands of years, and hydroelectric for over 100. But it has that huge downside of that you need to have, like a suitable river in a valley close to a population that wants to use it. And it's environmentally damaging and, very very expensive to build the infrastructure. So there is a possibility to take it off river, and anywhere you've got some elevation gain, you can put a couple of reservoirs at the top, at the bottom, and pump between them and get a big. Then at the top, we've got the famous Tesla battery, a Hornsdale battery in South Australia, and that was the one that was famous because there was some funny tweeting between Elon Musk and Mike Cannon-Brookes, who's an Australian tech billionaire, and they kind of took a very difficult political problem to, solve a problem with the electricity grid in South Australia, and solved it very fast through, a bit of, that magic that tech billionaires seem to be able to impart on ambitious project like that. And then at the bottom, I've got hydrogen, which, it's something that everyone's talking about a lot, and we'll see how much that has to play in the future energy storage mix, I think. Okay, so that's the electrification part. And electricity, to be honest, electricity is the easy part. Making green electricity is the easy part. This chart here, it has all the different kinds of, all the emissions in the economy, and how they might reduce to zero by 2050. And the blue part is electricity, and you can see that goes to zero a lot closer than others. And it can even eventually go to negative zero or negative numbers below zero if we start doing things like bioenergy with carbon capture or stuff like that. So that's the easy part of the transition. So what about the hard parts? That's what we need to actually address climate change to get us to zero. So this chart has all of the global greenhouse gas emissions by sector. There's a lot of information in there, but basically the hard parts are iron and steel, chemical and petrochemical, aviation, shipping, energy use in buildings, specifically the heating part, cement and livestock and manure. That kind of captures most of it. And there's still some easy wins in all of those industries, but those are the ones that really have some hard parts left. I'll just really quickly go through each of these and some of the ideas people are looking at to solve it. And just bearing in mind, it makes up like 10 or 20% of the emissions. So, you know, that the bulk of it we can get through pretty easy, mature, cheap technologies. So for building heating, moving away from gas, improving insulation is by far the most important and easiest, cheapest thing to do, but people don't for some reason. Then heat pumps, and people are looking at hydrogen, and I'm pretty sure we won't be using hydrogen for home heating if for anyone that cares about doing it in a cost-effective way. And we've got green steel. Again, hydrogen can be used to replace the coke that they use at the moment as a reduction agent. There's also electric arc furnace for recycling scrap and new electric process, molten oxide electrolysis. So that's an interesting area of development at the moment, and I don't know what's going to win, or maybe if it'll be a combination. And cement, which makes up, I think, 2% of the world's emissions, or more, if you depending on what you include. There's a bunch of different technologies I've got there, but it's the last one that I think is the most important. It's substitution. You don't need to use cement for everything that is used today. There's other materials that you can get the same properties for. One of the reasons why cement is used everywhere at the moment is because it's so cheap. So, if we were, for example, to include a carbon tax in the cost of cement, some estimates show that would increase the cost by about 50% just from adding the European price on carbon, for example. You'd get big changes just from encouraging people to consider whether they need to use cement for every application they currently do. Then livestock. It's a problem we've all heard, about methane from livestock, and it's obviously a much more potent, or at least of a short-term, greenhouse gas. So that's going to be one of the bigger challenges. And again, I think probably substitution is one of the biggest things that we'll have here if we can just eat less meat. That's definitely one of the biggest personal things that people can do. Then other than that, there's going to be a range of different ways to reduce the impact from livestock, and also start to use farms as a way for negative emissions through soil carbon and stuff. Then shipping, it's a range of options available. It's not the technology that's challenging, it's the economics. So shipping fuel is just so cheap. They really just use the literal bottom of the barrel, whatever anyone else doesn't want. So you could replace it with any of these fuels, but it's always going to be more expensive. And I think it will be. And I think that it will be substitution again for shipping. I think we'll start to see more, onshoring, I guess, the opposite of offshoring. I think we'll start to see more things manufactured where they're made. But yeah, other alternative fuels would be hydrogen, ammonia, biofuels, and then there's also some wind-powered ships, which is kind of cool, and back to old times again. And then aviation. Hydrogen is not coming anytime soon for aviation, but maybe in the 2050s could provide a long haul option. Electric is here now, but only for short haul, and will never probably do long haul. Biofuels can substitute, but are expensive. And then again, substitution, whereby I mean using trains, using video conferencing. I think aviation is just simply going to have to get a lot more expensive, and people are going to have to do it less. So yeah, looking forward, I'm optimistic. 2030s, costs taken care of, scale taken care of, availability taken care of, and climate change definitely on the way. That's the way I see it. And I know that I'm actually not an optimist by nature. I'm a pessimist. I spent my whole career being so pessimistic about our ability to solve this problem. Right now, I'm more optimistic than I ever have been. And I think it's a really, really good time to be involved in working professionally in the energy transition. So yeah, I'll leave it there. I think I've gone a bit longer than I expected it to. So I hope it was not too boring.
No, that was fantastic. Thank you so much. I really enjoyed that, and I have a lot of questions for you, and I know our audience will as well. So I'll save my questions for then. But I'll just say that for the viewers, if you're interested in learning more about the technologies, I highly recommend Rosie's YouTube channel if you'd like to know about why turbines have 3 blades and why they're front facing and all these other cool technologies that are coming out that are helping us to address the issue of climate change. Do take the time to check out her YouTube channel. Thank you so much, Rosie. I really appreciate you taking the time to talk with us today.
Yeah, no problem. Thank you for having me.
We hope you've enjoyed today's talk. Each of our talks is followed with a Q&A session that you can learn more about in the video description. If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.